concentrate on the topic that is a quantum computing and polynomial non-polynomial algorithms. That is part of the variants of the Turing machine and linear bounded automata of model 5. Of course, the course called Automata Theory and Computability for 5th semester. So here you can see the presentation flow. At the beginning we will going to be discuss the what is called linear bounded automata, and followed by the classes of polynomial and non-polynomial algorithms. So there is a continuation with the quantum computation, the quantum computers going to be discussed. So here we have discussed enough about the concept of what is called linear bounded automata and also variants of the Turing machines as a model 5 chapter name. So that concept name, that set of sensitive languages by the model, and infinite restricted into finite of the tape length. So that is Turing machine model. So automation, because the linear function is decides the length of the tape. So the model of linear bound and developments of the relation between the linear bound automata, that is a sensitive languages. It should be noted that compiler language will be light between this sensitive and context free languages. Is a ND non-deterministic Turing machine which has a single tape and length is a infinite but not infinite. So that is bounded by the linear function. Coming to the quantum computers. Computers are physically objects. So is a physical process. So what computers can or cannot perform to determine the laws of physics alone, not by pure mathematics. The laws of physics also the pure mathematician. So can or cannot by the computer. Computation with the coherent atomic scale dynamics. So that coherence scale dynamics is possible with help of the computers. So behavior of quantum computers is governed by laws of the quantum mechanics. So in 1982, Richard Feynman, a Nobel laureate in physics, suggested that to build a computers based on the quantum mechanics, you can build a computers. Quantum mechanics arose in 1920 when classical physics could not be explained everything. So that was a dark side from the classical physics. So during that time, they evolved the quantum mechanics, which able to provide some light on the dark side of the classical physics. Quantum mechanics will provide tools to fill up the gulf between the small and relatively complex systems in a physics. So there is a small and very complex big systems are there. So there is a gap between these two. So that can be a gap, and also unanswered questions will be there. So this gap, and while answering suitably, so that gap is filled by quantum mechanics. So that is the potentiality of the quantum mechanics even before that classical physics. So 0 or 1, that fundamental notations, concepts of classical computation and information. That is zeros and ones is the computer. Also classical computers is built from electronic circuits, which comprises wires and gates, logical gates and OR gate. Again, gates will be with help of the transistors and diodes, right? So these are all classical, right? So let us study quantum bits, which are bits will be going to be used in a quantum computers. Quantum circuits, which are analogous to bits, classical circuits. It is analogous to quantum circuits is analogous to the classical circuits. So quantum bits going to be considered, that is a simple qubit can be described mathematically. Bit 0 or 1 is the fundamental concept of the classical computer circuits or information. So these bits are playing a vital role in most of the today's even fast computers, right? So those bits we can also consider in a quantum computers. So classic computers built from electronic circuits employing the wires and gates, and quantum bits and quantum circuits which are analogs to bits and circuits, that is repeated. So quantum computers, there is a two possible states, that is a qubit, that is direct, or quantum bit is a qubit. Two possible states of qubit, the direct, that is a qubit, quantum bit is a qubit. So described mathematically, where alpha is a complex number, using the alpha they are going to be express this mathematically. So that alpha naught or 0 is greater than alpha 1 or 1, right? Alpha naught is greater than alpha 1, where alpha naught is 0 and alpha 1 is a 1, which is greater than, right? So qubit can be infinite number of states other than direct, that is a slash 0 greater than or slash 1 greater than, slash 0 greater than or slash 1 greater than, that is a qubit, infinite number of states. So operation are induced by the apparatus linearly. This is induced by the apparatus linearly. So that is if 0 1 0 0 1 1 1 1 2 1 0 2 0 I1, that is also 1. Computation, Dutch proposed Dutchess proposed the first blueprint of quantum computer. So a single qubit can be stored states 0 and 1 in quantum superposition. Adding more qubits to the memory register will increase the storage capacity exponentially. Adding more qubits to memory register will increase the storage capacity exponentially. When this happens, exponentially complexity will reduce to polynomial complexity. So superposition, adding more qubits to the memory register will increase the storage capacity exponentially. So this exponential behavior, it is almost going to be very costlier. It is higher than the polynomial. When this occur, exponential complexity will reduce to polynomial complexity. So Peter-Shor's algorithm explained to hope that quantum computation may work efficiently on the problem of exponential complexity. So exponential complexity algorithms are inherently costlier for the most of this our digital computer, right? So that Shor's narrated computing, that to quantum computing may efficiently work on these such problems, exponential complexity. So but problems arise at the implementation stage. Theoretically it is true, exponential can be solved when more interesting qubits are involved in a circuit. Invite the more qubits in order to solve exponential complexity problems. The surrounding environment is affected by those interactions. Sorry. So the surrounding environment bits are going to be impact or disturbed by those interactions, right? This due to the exponential behavior that interacting qubits are involved in a circuit, so it is difficult to avoid them, that affecting the surroundings environment, that is more difficult to prevent. Also, quantum computation will spread outside the computational unit, will cross the boundary, it go beyond the computational unit. It will irreversible dissipate useful information to environment. Uh, it will go beyond computation unit and will be irreversible. This irreversibly dissipate useful information to the environment. So, computing, this process is called decoherence. 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 The problem is to make qubits interact with themselves but not with the environment. So more bits are going to be interact with the environment, but this interaction it should happen only the qubits of that. It should not go beyond the boundary outside that. So outside that is an environment. So it should be only interact with the qubit itself. So some physicists are pessimistic and conclude that efforts cannot go beyond few simple experiments involving only qubits. So those qubits which are going to be interact with the environment, so those only we need to be address. Those we need to be take care. So some physicists still they are pessimistic. They are telling that, but some researchers are optimistic and believe that effort to control decoherence will bear fruit in a few years rather than the decades. So it is quite natural. It may going to be get a solution in the earliest. It remains a fact that optimism, however, overstretched makes things happen. Over elaborated makes things happen. Over exaggerated makes things happen. The proof of Fermat's loss theorem and four color problems are examples of this. So Fermat loss theorem and four color problems are the evidences to happen that overstretch making things happen. Thomas Watson, the chairman of IBM, predicted in 1943, he said there is a world market for maybe 5 computers. So there is a world market for maybe 5 computers are enough. So that may be from quantum computing. But the growth of computers has very much surpassed his prediction. So class P, that is a polynomial problem. So here the class P, a decision problem D is solvable in a polynomial time. A decision problem D is solvable. How much time? That is a polynomial time or in the class P. So the decision we can solve with the polynomial time. That is problem. If there exists an algorithm A such that A takes instance of D as inputs, A always outputs the correct answer, yes or no. A, D as input and produce the output, that is a correct answer, either yes or no. No in between, no hanging, no looping, infinite looping, no halting problems, right? So that is always the outputs that correct answer. So that is going to be extended. There is exist a polynomial P such that the execution of A on input size n always stops in a P of n or lesser steps. So inputs of size n always terminates in phi of n or fewer steps. So there is exist. So if so, example, the minimum spanning tree problem is a class P, is a polynomial problem. Minimum spanning tree. So we can, in the shortest distance, we can visit all the trees of the, all the nodes of the tree. So that tree may be example of the, see, reaching the places of business places or any traveling salesman problem or so on. That is, so that MST, that a minimum spanning tree we can obtain, so that the cost of the distance we can measure. So for any given tree we are able to get a MST, that is a minimum spanning tree. From that we can understand the, we can decide the cost of the tree for communication or for traveling or goods transmission, so on. That is, so that is a word class problem. The class P is often considered as a synonymous with a class of computationally feasible problems. Polynomial problems or polynomial behavior algorithms are computationally feasible problems. In other words, those are solvable. So their cost is reasonable. So their cost is quite we can bear that cost. So bear that cost. So the computer will be exploit such problems and able to provide solutions. So that is a polynomial behavior synonymous with the computationally feasible operations or solutions, that is. So having understood this, although in practice this is somewhat unrealistic, so sometime is a unrealistic, that the polynomials problems. So we have, when it become unrealistic, that may go to close to non-polynomial, non-deterministic polynomial, non-polynomials. So which are beyond the polynomial, it may be exponential. So it may be heuristic also. Tenzing climbed the Mount Everest. So that is a heuristic. So beyond polynomial. So that is a very costlier algorithm. So class that NP. So decision problem is a non-deterministically polynomial time. Non-deterministically polynomial time solvable, or in the class NP if there exists an algorithm A such that, if there is an algorithm exists that, so A takes the input potentially witnessed for yes answer to problem D. So it is a more realistic witness or potential answer for the yes, right, for the problem D. So a correctly distinguished true witness from the false witness, the accurate discrimination, true witness from the false witnesses. So we can get some filtered output. So continuation of this class NP. So we have there exists a polynomial P such that for each potential witnesses of an instance size of n of D, instance of n of D, the execution of the algorithm A takes at most P of n steps, maximum P of n steps for the n input of the D, that is a P of n. P of n steps is essential. Think of non-deterministic computer as a computer that magically predict a solution, then has to verify that it is correct. Verify that it correctness you need to be verified. If a solution exists, computer always predict it. Solution exists. One way to imagine it, a parallel computer that can be freely spawn an infinite number of processes, freely spawn or create fork the processes, infinite number of processes. So that is a one way of imagination. One way of imagination that if we have a solution, then it may be possible to predict it. Solution exists in the literature, or it is a possible feasible solution from the computer. It going to be predict or guess it. One evidence we can observe, so that is a parallel computer able to generate infinite number of processes, right? So those processes going to be involved to perform the minor tasks. Yeah, one processor work on each possible solution. So infinite number of processes are there. So infinite the job going to be task going to be executed possible from the this one processor. So all processor attempt to verify that there is a solution works, right? So all the huge number of processor are going to be take a birth in a parallel computing environment, and each process going to be look after the particular task, and the multiple tasks or huge number of tasks or countable number of tasks sometimes, right? So those going to be solved by this processor, and is going to be provide a solution. All processor attempt to verify that there is a solution works. So if processor finds it has a working solution, finds it working solution is visible or noticeable here, then so NP is equal to problem verified in a polynomial time, right? So from this evidence that parallel computer going to be most of the ways of parallel environment going to be generate the infinite number of processors. So that infinite number of processors going to be solve the various tasks that even in uncountable number of tasks. So this non-polynomial. So non-polynomial is equal to problem verifiable in the polynomial time. So having seen this, unknown whether P is equal to NP most suspect not. Unknown whether P is equal to non-polynomial. So most suspect not. So NP complete problems. So we have seen the relation of this P and NP. We have seen the boundary of this solution space for the problem from the P side and also NP side. So one evidence we've seen from the parallel computing environment, and NP, the complete problem are that hardest problem in the NP. NP complete problems are the very tough problems in the non-polynomial. If any one NP completes problem can be solved in a polynomial time, either this parallel environment or maybe quantum computing or any other physics solution that is able to provide that, so that can be polynomial time, then every non-polynomial complete problem can be solved in a polynomial time, right? So can be solved, and it may be a way to solve the other problem also. In fact, every problem in a non-polynomial can be solved. Every problem in a non-problem can be polynomial time solved, which would show that P is equal to NP. Can be so that which would P is equal to NP. So thus the solve Hamilton cycle in a big O of n power 100, n power 100. So solve Hamilton cycle big O of n power 100 time. It is proved that P is equal to NP, that is polynomial is equal to non-polynomial, that is a non-deterministic polynomial. Retired, rich and famous. Retired, rich and famous, that is a n is P is equal to NP. So NP complete problems. So the crux of NP complete is a reducibility. So reducibility. So the complexity or the solution space domain or solution space we can split into the final level, that is reducible. So informally problem p can be reduced to another problem q. So can be reduced to q if any instance of p can be easily rephrased as an instant of q, the solution to which provide a solution to instant of p. So that p and q are what to do. Suppose easily means this is rephrasing is called a transformation. You can transform the bigger problem into smaller problem. So transformation. Intuitively, if p reduced to q, p is no harder to solve. P reduced to q, p is no harder to solve than q. So example, p given a set of booleans is at least one true. At least one true. At least one true, that is. So given a set of integers, is there some positive? Some is positive, some may be negative, some may be 0, but given a set of integers, is there some is positive? So transformation have x1 to x to y, that is x1, x2, x3 to xn to y1, y2, y3 to yn, where yi is equal to 1 if xi is equal to true, yi is equal to 0 if xi is equal to false. So yi 1 if xi true, yi 0 if xi false. yi 0 xi false. So this transformation leads to the example, that is a linear equation to reducible to solving quadratic equation. So how can we easily use a quadratic equation solver? How can you easily use the linear equations? So given one NP complete problem, we can prove many. We can prove all interesting problems NP complete. So that is a graph coloring algorithm is equal to register allocation. So register allocation in a CPU, it allocates the register for the demands of this various other devices. So graph coloring is a NP complete problem. So Hamilton cycle and path is also NP complete. So knapsack problem. So filling the gold dust into the bag. So thieves stolen the gold dust, so they can fill their bags with the gold dust, so that we have maximum weight and easy to carry. So maximum weight, so that it is a cost releasing factor, and easy to run away or easy to carry. So traveling salesman problem, it may be a two-dimensional, it may be a three-dimensional, right? So that traveling salesman problem could be going to be NP complete problem. So job scheduling with the penalties. So job scheduling, maybe CPU scheduling, or maybe round robin, or first in first out, or first in last out. Various are there with the penalties. Memory cycles more, then penalty will be there. That is a miss occur, cache miss occur, or the main memory miss occur. That case we have to bring them. Not to bring, we have to spend more cycles, memory cycles. So that is in terms of the penalties, etc. So NP complete. So you can see NP hard, right? So NP hard. So optimization problem whose decision versions are NP complete are called NP hard. Optimize this problem, that is a bundle of solutions. So those we need to be optimized whose decisions versions are NP complete. NP complete or NP hard. So complete solution will be there, so that we can as a NP hard. Theorem. If there exists a polynomial time algorithm for finding a optimum in a non-hard NP hard problems. So polynomial time for NP hard problems, P is equal to NP. That is a theorem. P is equal to NP. Then the polynomial time algorithm we can solve with help of the problem. We can solve with the polynomial time. Then the optimum, finding an optimum in any NP problem is a P is equal to NP. So here the proof, that is let E be an NP hard optimization. Let us say minimization problem, and let A be the polynomial time algorithm for solving it. Right? A B and E be a NP hard optimization. So now instance J of a corresponding decision problem D is of the form I comma C. I is an instance and C is a number. C is a number. I is an instance and J is a number. So then the answer to D for instance J can be determined by running A on I instance, that is, and checking whether the cost of the optimal solution exceeds C. So C is a number, so that cost whether it is exceeds or not, that we need to be observed. So that we need to be decide, checking whether the cost of that optimal solution exceeds the C. So thus there exists a polynomial time algorithm for D. Solution exists C, there is exist, and NP completeness of letter implies P is equal to NP. Polynomial is equal to NP. So the overall idea here is, if any problem or solutions available for polynomial time, for that polynomial time, that is a P, and there is also solutions for the optimized non-polynomial solutions can also provide with this polynomial time. So there is a bunch of solutions for non-polynomials. So certain portion we can solve with the non-polynomial, and other portion also we can also solve with the non-polynomial. Certain portion is possible to solve with the polynomial, then whatever the remaining portion or complex portion, it is also quite possible to solve with the polynomial. So that is a concept behind that there is exist a polynomial time algorithm for determining the optimum in any NP hard problem. So that is a P is equal to NP. So from this material we can obtain from the Lanrich Automata Computability Complexity, that Pearson Education publisher, and material drawn from Misra and Chandrasekharan. So that is Theory of Computation of Prentice Hall of India. And also there is other books called Motwani, Ullman and Hopcroft, Introduction to Automata Theory, Languages and Computation. So third edition, Pearson Education. So Michael Sipser also provided the reference book, Introduction to the Theory of Computation, third edition, Cengage Learning. John C. Martin, Introduction to Language and Theory of Computation, third edition, Tata McGraw. And also the magazines and papers, internet, help us to collect more material, right? So this is some reference and textbooks from this. So thank you for patient listening. The topic classes of P and NP problem, and quantum computation and quantum computers. So from this, so the session ends. Thanks to coordinator, moderator and subjects expert. Thank you once again. Thank you one and all.